today I want to talk about friction. All right. We have been talking about, so far there were only four forces that we were taking them into account when we were drawing a free body diagram, or we were analyzing any system, machine or frame, or any structure. And those first forces were weight, force of a spring or in a spring, ropes, pulleys, ropes, wires, chains, and a system of pulleys that we talked about, and the smooth contact. Right? Smooth contact plus supports, and different types of supports that we talked about when we are drawing free body diagram or we're analyzing a rigid body. Right now, today we're going to add another force to this category, and that's friction. Now, what friction is, that's basically going to be the topic of today's class, and whether it's a good thing or bad thing, we'll also talk a little bit about that. So friction, I did bring these photos. I think most of them are coming from your textbook. I'll talk about them, but let's start first. Let me put the title here. We're talking about friction today. All right. Now, what is friction? All right. So if I want to give you a general definition, I would say friction is a force that resists the movement of two contacting surfaces that slide relative to each other. Right? You have two surfaces, they slide relative to each other. One could be fixed and the other one is sliding on top of this one, or both of them could be sliding relative to each other. Right? Friction is a force that resists this movement, wants to stop this movement. Right? So it exists in nature. We have to take it into account. Right? So let me just put the definition here before I go further. So friction is a force that, let's say, resists the movement of two contacting surfaces, let's put it this way, that slide relative to one another. Right? Since it's a force, we know, we already talked about this, force is a vector, so we have to decide about its magnitude and its direction, right? We'll talk about this magnitude later on, but generally speaking, in terms of direction, right, friction is always tangent to the surface of the to the surface at the points of contact, right? If you have two surfaces, you know, wherever they are in contact with each other, that's right, friction is tangent to this surface. So that would be the line of action for friction, tangent to the surface at points of contact. Now, if you know the line of action, how about its direction? Well, the direction of friction force is always in a way that is trying to stop the motion. So it's opposing the possible motion or existing motion. So if I have two surfaces, they're not moving with respect to one another, but let's say I'm applying a force and I know that by applying that force, the top surface is going to, let's say, go to left. That's a possible direction of the motion. So the friction would be in the opposite. The friction should be put there in a way that is opposing this motion. If they're moving with respect to each other, obviously, if, let's say, if this surface goes to the left, friction should be directed to the right, always opposing the motion. Right? That's basically what direction does. It's always trying to stop the motion in nature, right? So let me put these two also here. These are the things I want you to know about friction before we get into what is the magnitude of friction, which is, we're talking about this direction. So it always acts, let's talk about the line of action first. So acts tangent to the surface, better to say, at the points of contact. You'll see it could be one more than one point. So that's the line of action, right? It's tangent to the surface at the points of contact. In terms of direction, it is directed to oppose, let's put it this way, the possible or the existing let's see, existing motion between the surfaces. All right, so line of action and its direction. We settled that, right? We'll clearly talk more about this later on. Now, I brought this figure here because I wanted to give you some idea about whether we want friction or not, right? Friction is a kind of force that actually takes the energy out of the system. So it takes the energy out of the system, and what happens is that it converts the energy always into noise or heat, right? A good example of that when you're rubbing your hands together like this, right? See, you start hearing a sound. This is friction taking energy, the energy you are putting into this when you're rubbing your hands. This is your body's energy. It is converted into heat. Your hands start feeling warm, right? And it creates sound. So this is the general rule. Friction takes the energy out of system and converts that into heat and or sound, both. Right. So generally speaking, we don't want friction in so many cases, right? Because we don't want the energy to be wasted. You know, when you put energy into something, you want that energy to be used for whatever purpose you're putting that energy into a system for. So, however, it's not a general rule. The example of the car is a good example. If you look at different components in a car, right? Let's just start with somewhere that we don't want friction. The good example of that would be a car's engine, right? If you think about the pistons moving inside the cylinders, right? We are we are basically putting gas in our car, burning the gas and using that energy to make these pistons move, so we can use that energy to turn the wheels and make the car moving, right? Now, what happens is that we don't want friction between these pistons or moving inside the cylinders, right? So where there is a contact, there is a friction. So since there is a contact between pistons and cylinders, or inside the cylinder, there's a contact between the piston and the cylinder, inner wall of the cylinder, right? We want to minimize that friction. That's why we lubricate engines, right? Piston and cylinders. We keep them very well oiled because we want to minimize friction. Why? Because we don't want the energy that we are getting from burning gas to be wasted overcoming the friction. We want this piston to go up and down very easily, so it can turn the shaft and we can actually use as much energy as we can get from the gas we put in the car to move the car. And so we want minimum friction there. That's why we lubricate that. Now, if you think about brakes in a car, like, we want a lot of friction there. Why do we want it? Because friction is something that is taking the energy out of the system, and that's what we want in that case. When you push the pedal, like when you push the brake, you want your car to stop. So when brake pads come into contact with discs, right, that's where you want maximum friction, because you want this friction, the friction between brake pads and the disc, to stop. You want that friction to stop your car from moving. You want the energy that the car has when it's moving be taken out of the system, so the car stops. Another example, a very tangible one, would be the friction between your tires and the surface of the road. You want a lot of friction there, because friction is something that keeps your car on the ground. So what we do is that we want to increase that friction, and that's why it's not a good idea to go fast in a rainy day or when the surface of the road is covered with ice or snow, right? Because those are some things that reduce the friction, and we don't want that. We want maximum friction between tires and the road in so many cases, because it gives more stability to the car, and it keeps the car on the ground, on the ground, so it's more safe. In a belt, right? Belts are, you'll see and deal with belts way more often when you take machine design the course, and you probably also study how to design belts. Belts are something that we basically use to transfer energy or power, better to say, from one shaft to another, right? Instead of having a bunch of gears next to each other, you can use a belt to transfer power from one shaft to another shaft. Now, what happens is that you want a lot of friction between the belt and the shaft. You don't want your shaft to slide on, or the belt to slide on your shaft, right? You want, when your shaft turns, you want your belt to move with it. So you want maximum friction there. If the friction is low between the shaft and the belt, right, shaft keeps rotating while the friction is not, while the belt is not moving, which is not something you want. You want, for every turn you have in this shaft, you want that power to be transferred to the other shaft through this belt. So you want a lot of friction there. So it really depends on what the purpose is. If you're sanding a surface, right, you're trying to flatten some surface or make it more smooth, right? You want friction there. You want friction to take particles off that surface. Right? So that's another place that you actually want friction. So it really depends on the purpose and the application and the machine or the mechanism you're designing. Friction could be a good thing, could be a bad thing. It could be something you want to get rid of, could be something you actually want to maximize. It really depends on the purpose of that structure or frame or machine. Now, better to say machine. Frames don't really move, that components don't move with respect to each other. Right? Typically, we're talking about machine here. Now, we talked about the direction of friction. It's a force. It's always tangent to the surface at points of contact, and the direction, that's the line of action, and direction is always in a way that is opposing the existing motion or possible motion. Now, the next thing you have to figure out is that what is friction, and since it's a force, what is the magnitude? Well, we talked about what friction is. We want to figure out the magnitude. How can we calculate the magnitude of friction, right? As we said, force, every time we tell you force is a vector, has a magnitude and direction. This is the direction we talked about. Now we have to talk about the magnitude and how can we actually calculate the magnitude of friction. Once we do that, we are able to actually draw a free body diagram now with 5 forces. 4 forces we know from before, plus friction. And then analyze the systems that the friction is not negligible, and we have to friction into account for those systems, definitely, to get the correct